This is Professor Steven Sakula. I'd like to welcome you to this online lecture. This is part one of a two-part lecture on the movement of electric charge. Now to begin today, I want to start by thinking again about what a point charge does in the presence of an electric field. Let's keep things simple. Let's consider a uniform electric field. Presumably this is being created by some nearby charges, perhaps a large infinite sheet of charge, as I talked about in my mini lecture. That creates a nice uniform electric field. And let's imagine that we have a positive electric charge whose charge Q is a number greater than 0 coulombs. What's going to happen to that charge? Force causes matter to accelerate. That is the essence of Newton's second law. F equals ma. An electric field is a field of force that acts on electric charge. We have a positive charge sitting in a uniform electric field. Now we can write that electric field E vector, because it's uniform, as a number whose value is positive. We'll call that the magnitude of E, and that's a number greater than 0. And for the purposes of this illustration, we'll say that it points in the I-hat direction. So we'll define a unit vector that points along with the field, and we'll call that I-hat. So the x-axis, essentially. That's our electric field vector. Its strength is the same everywhere, independent of where you are in space. And that's what makes it a uniform field. Now, we know from the general definition of the electric field that it is equal to the force acting per unit charge in the field. In this case, our unit charge is our little positive charge here, Q, whose charge is a number greater than 0. And so we can take Newton's second law, which simply says that matter being acted on by force changes its location in space in response to that force. We have here a relationship between electric field and force, and we can substitute. We know that the force acting on our charge Q due to this uniform electric field is equal to Q times E vector, which is Q E magnitude I hat, and that must be equal to ma vector from Newton's second law. Let's rewrite and solve for the acceleration. The acceleration of our positive point charge is simply going to be equal to its charge divided by its mass times the magnitude of the electric field times I hat. Q is a positive number, mass is a positive number, the magnitude of the electric field is a positive number, and I hat points in the positive x direction. We see that there is nothing that multiplies I hat that changes the sign of the vector. And so, for a positive charge, we have the situation where the acceleration points in the direction of the electric field. For a negative charge, the opposite is true. We can write, if we put a negative charge in here, we can say that its charge is equal to negative Q. So let's imagine that our positive charge and our negative charge have the same magnitude charge, Q, but the sign of the negative charge is opposite that of the positive charge. And so all we have to do is substitute negative Q into this equation. All the other numbers are positive, and so we see that the net effect for a negative charge is to create an acceleration that points in the direction opposite the electric field. Now, we've discussed this before. There aren't any huge surprises here, but this will come in handy in the next part of the discussion. Now, what happens if instead of a point charge, you have a dipole? A dipole consists of a positive charge and a negative charge. They have the same magnitude but opposite sign. So here is our charge plus Q, and here is our charge minus Q, where Q itself is a number greater than 0. We know that the dipole can be characterized by the dipole moment, P vector. Its magnitude is equal to Q times D, where D is the length of the dipole from the negative end to the positive end. And P hat, a vector that points from the negative charge to the positive charge, P hat. Now, let's think about what's going to happen to this dipole. Imagine that it is oriented relative to a uniform electric field, E vector, just like in the previous slide, but that orientation is not parallel. That is, its dipole moment, P vector, makes an angle theta with respect to the electric field. So initially, the dipole moment is oriented off the lines of electric force at an angle theta. What's going to happen to it? Let's draw a picture on the next slide. So here again, I'm going to simplify my picture of my dipole moment by just drawing it as a line whose length is d. And let's imagine that there is a central point on the line, halfway along the length. If we have a force due to an electric field acting in this direction, that force on the positive charge is going to tend to cause this dipole to rotate around the center of rotation in a clockwise fashion. Why? Because the force acting on this positive charge is going to point to the right. And if we think about what's going on with the negative charge, well, it's also subject to the same electric field, E vector, but we know that it's a negative charge, so the force on it points in a direction opposite the electric field. And so you have one force tugging to the right on the positive charge, one force tugging to the left on the negative charge. This causes, in both cases, a clockwise rotation of the dipole around the central point of the dipole axis. When you have a rotation, you have a torque associated with it. Remembering that the definition of torque is equal to the cross product of a vector r with your force vector, you can then start to think about what the total torque is on this dipole system. Alright, well, if we're going to attack this problem, we need to do it in pieces. So what the heck is r vector in this problem? For rotations, the vector r always points from the center of rotation out to where the force is being applied. So in our problem, we have two r vectors, r plus and r minus. Each of them gives an associated torque. So there's a positive torque associated with r plus, cross product with the force on the positive charge, and there's a negative torque associated with r minus vector and its cross product on f minus. Okay, well, now we have two problems to solve. Very briefly, let me review the salient features of the cross product. If you have two vectors, a vector and b vector, and you take their cross product, you will always get a third vector, let us call it c vector, in response. C vector is perpendicular to a vector, and c vector is perpendicular to b vector. That's a feature of the cross product. It always produces a third vector, c vector, that is perpendicular to both of the original vectors. In addition, the magnitude of c vector, which I'll just write as c, is equal to the magnitude of a times the magnitude of b times the sine of the angle between them, theta. What does this imply? Well, if a and b are parallel, that is, the angle between them is 0, then the magnitude of c vector is also 0, because the sine of 0 is 0. If you have two parallel lines, you cannot have a vector that is uniquely perpendicular to both of them, and therefore c vector is null. If theta equals 90 degrees, sine theta is equal to 1, and c is just equal to a times b. That's the maximal value that c can ever have. Now, keeping these little features of the cross product in mind, let's return to our torques. Let's chop the problem into more pieces. First of all, r plus vector. What is that going to be equal to? Well, it's going to be equal to the magnitude of r plus and the direction of r plus. What is the magnitude r plus, and what is the unit vector r plus hat? The magnitude of r plus is just half the length of the dipole, 1/2 d. The unit vector is a vector that is parallel to the dipole moment vector, p hat. And because unit vectors all have length 1, r plus hat and p hat are equivalent to one another. So we can simply write r plus as equal to 1/2 d times p hat. What about r minus vector? R minus vector has the same length as r plus, but it points in the opposite direction. So we can write it as 1/2 d negative p hat. Excellent. Now, let's think about what the force is on both of these. The force on the positive charge, F plus vector, is going to be equal to Q times E vector, the electric field vector. And we can write that as Q times the magnitude of E times I hat, which is the direction that the electric field points in. What about the force on the negative charge, F minus vector? Well, that's going to be equal to negative Q E vector, which is equal to negative Q E I hat. And so now we have a situation where we have two torques. The torque on the positive charge, we can substitute our pieces in. That's going to be equal to 1/2 d p hat cross Q E I hat. And we have torque on the negative charge. That's going to be equal to negative 1/2 d p hat cross negative Q E I hat, which is just equal to 1/2 d p hat cross Q E I hat. That's because the minus sign here and the minus sign here multiply and cancel each other out and give you a positive sign. So lo and behold, we have two torques, the torque on the positive charge and the torque on the negative charge, and they're identical to one another. They have the same magnitude and they have the same direction. And you should have been able to see that, because if both torques act to rotate the dipole clockwise, they must necessarily be vectors that point in the same direction. So since we have two torques, we can add them together to get the total torque. The total torque is equal to the torque on the positive charge plus the torque on the negative charge, and that's going to be equal to Q d p hat cross E vector. Well, what's fascinating about this is we have this thing here, Q d p hat. And if you remember, the definition of the dipole moment itself was Q times d times p hat. And so the total torque on a dipole in a uniform electric field is simply equal to P cross E vector. This is a very nice result. We have this bulk property of the dipole that we've assigned to it, that is the dipole moment, and if we just take the cross product of that and the electric field, we immediately get the torque on the entire dipole. And this is why the dipole moment is so useful. If you can measure the response of a molecule to an electric field, you can get its dipole moment, P vector, and immediately you can really start characterizing the properties of the dipole without having to measure all the individual bits and pieces of its charge distribution. In the next part of the lecture, we're going to take a look at what happens when lots and lots of charges, let's say Avogadro's number, get exposed to an electric field in different kinds of materials.